Okay, so continued from the previous example, we are going to consider the same investment. Like forget about the commission, forget about the fee, but instead we are going to scale up the investment by 10 times, like buying 10 times more assets, right? Um, and then, so minus $10 becomes minus 100, and $20 becomes $200. So probability the same, but the outcomes increase like multiply by 10. So in this case, also like you need to find the variance first. Do the exercise again and see what is the variance. Okay, so if you have not finished your work yet, pause the video now. I'm going to turn the page. So the first thing we have to do is to calculate the mean. We have done this many times. Multiply the outcome to the probability, minus 20 and 10 and 80. So sum the probability weighted outcomes, and then we get 60. So 60 is the mean. And remember, in our original example, the mean was $6. Now, everything is multiplied by 10, so the mean is also multiplied by 10. And remember, multiplying 10 is a linear transformation, so mean also preserves the same linear relationship. So mean is also inflated by 10 times. Okay, so this is just the first step. And then next, using the mean 60, calculate the deviation, and then calculate the squared deviations. So this is inflated outcomes inflated by 10 times. So subtracting 60 will make deviations like this. And remember, I will compare them again. Remember, minus 60, minus 160, minus 60, 140. Compare that to these numbers. So the deviations are multiplied by 10, which is natural. Everything was multiplied by 10, so the distance is also multiplied by 10, right? However, what's interesting, what's not natural here is when you square the deviation, it is like say 25,600. Like remember this number, compare that to here. Previously, the first squared deviation was 256, but now it has two more zeros. 2 zeros multiplied by 100, not 10. And this is because we squared the deviation. So deviation is multiplied by 10, and then you square them. That is, multiply times 10 becomes times 10 squared. So times 100. So squared deviations are inflated by 100 times, which is square of the original multiplication. This will make a difference. This will result in variance 14,400. Remember earlier, the original variance was 144, but now it is 14,000, so two more zeros. The variance is still 100 times larger, not 10 times. So this is another interesting observations. In the beginning, we multiplied 10 to all the outcomes, so it looks like everything is multiplied by 10. But in the end, it turns out that the variance is multiplied by 10 squared, because of the step of taking squares. So it is unnatural. Then in sum, this is an interesting result. Let's compare three examples together. This was the original example, and this is the second example where I considered $1 commission. And this is the last example where I considered like increasing by 10 times, like multiplying by 10 times, right? So then in each example, we calculated the mean and variance. The mean and the variance. So in the second, when you compare the first and the second, variance is the same. -1 does not affect the variance. I explained why. Everything moves parallel, so the distance does not change. So like the distance is here, and if they move together, distance does not change. So variance is not affected. Only the central location changes. It's a matter of location, parallel shift. But when you multiply 10, then the mean also multiplied by 10. The center, the mean, is also multiplied by the same 10, but the variance is multiplied by 100, right? So you see some kind of pattern. The mean behaves really well. So in the previous chapter, I explained the property of a mean for when you have a linear transformation. When you learn that result, you may think it's obvious. It's too obvious result. But actually, that was a very special result. So when you compare the properties of the mean and the variance, now you see how nice the mean is. Mean is really well-behaved measure, so it's much easier to handle. But the variance is not. Variance does not change when you add or subtract something, but and then it inflates too much when you multiply something. So that is a problem. Here is a general result. So like think about a linear relationship as before. So suppose that you have an original random variable x. X is an original random variable, and on to the original random variable, you manipulate by multiplying a and adding or subtracting something, right? B. Then you get a new random variable y. Then our question is, what's the properties of the mean and the variance between the new and the original random variables? Like this. The mean, the expected value is really well behaved. Like it behaves really well. Like mean of the new variable follows the same relationship based on the mean of the original variable. So mean is nice. However, the variance is not. So when you add or subtract something by plus b has no effect. Like adding or subtracting something has no change and does not make any change on the variance. Simply, right? And multiplication, multiplying a, not only just multiplying to the multiplication to the variance, but squared. The scale is squared, so it's also distorted somehow. This is not ideal, right? So we will define another random variable. The main problem here is, so actually the b disappears here. That is not a problem. That is more intuitive. It's like it's more intuitively understood. But the problem is a squared. If you multiply something, if it's squared, then it causes more algebraic problems. So what we are going to do here is we are going to take the square root again. So the problem arises because we squared all the deviations. So we squared all the deviations in the steps in one step. So what we are going to do is, in the final step, we are going to take the square root of the variance. Again, scaled up by squaring, and then bring the scale back by taking square root. That is the standard deviation. Maybe, you have heard about this. So this is also a measure of variability. Taking a square root is not a big difference, but in the end, it is a unit consistent measure, which is a big problem, like big difference. And the standard deviation is denoted as STD of random variable x, or simply sigma, or lowercase s. So because standard deviation is denoted as sigma or s, that's why the variance was denoted as sigma squared or s squared. So in practice, standard deviation is as important as the variance, and like practically it's actually more important because variance has like an undesirable property in this, like this. So then from the example, we can easily calculate the standard deviation because we already have the variance. Variance was 144 in the original example. If you simply just take the square root, then it becomes 12. Second one, the same. And the last one, 14,400. Take square root, use a calculator, then you will get 120. And then, as you can see, standard deviation is 10 times larger than the previous examples, which is exactly what we wanted. So everything was 10 times inflated. So standard deviation inflated by 10 times is a natural thing. It's the desirable scale. So that's why we love standard deviation. We use standard deviation rather than the variance. And the formula formula for the standard deviation can be written this way. Variance, when you have a linear transformation like this, we had variance in this weird relationship, but by taking square root on both sides, you have standard deviation here, and a squared becomes the absolute value of a. So this is because a may be a negative number. If a was -1, for example, then multiply -1 is like flipping, like it's taking the mirror image, flipping the right and the left. So distance does not change. It's just symmetric about the center. So distance does not matter, does not change. So we only take the absolute value, right? In distance, the sign does not matter, only the scale matters. That's why we have the absolute value of a here. So this is the standard deviation, which is a kind of just automatically follows from the variance. So simply speaking, how to calculate the standard deviation? First, calculate the variance, and then take a square root. That's it. So then if you ask how to calculate the variance, I told you, look at the previous slides, and then you know how to calculate the variance. By the way, also, the standard deviation has two different formulas: sample standard deviation formula and population standard deviation formula. The difference is coming from the variance. So if you calculate the variance using the sample variance formula, then the resulting standard deviation is a sample standard deviation, right? If you use the population variance formula in this step, then the resulting standard deviation is a population standard deviation. So it's intuitive, right? So standard deviation is actually the main measure used in practice because it has more nice properties than the variance. But both are important. Variance is still very important in many analytic methods. So, and the switching between them is pretty simple. Just take square root or take square, then you may switch between standard deviation and the variance. Okay, in the next slide, next video, I'm going to discuss a little bit about the standard deviation, how to interpret, how we use standard deviation. Okay, see you later.